Hi, everybody. Welcome to Orgoland in 3D, the sequel. Yes, past chapter 6, we dive into all this crazy other spatial 3D stuff in chapter 7. So I thought I'd start off with a little information about glucose.
Sugar, oh honey, honey, you are my candy girl, and you got me wanting you.
Yes, sugar, glucose. Yes, my favorite, one of my favorite drugs of all time is one of the key focuses of the beginning of chapter 7. So the reason why is this gentleman over here, Emil Fischer, spent his life's work studying sugars like glucose. And imagine he was drawing these organic chiral molecules that have chirality all over the place. So he kept having to draw tons of wedges and dotted lines. And all those wedges and dotted lines kept driving him bonkers. So of course, the mother of invention, he decided to come up with something a little better, a little easier for him to visualize, and hopefully for you to visualize as well. Another way to see our molecules. So his main premise and thought was, when I look at a chiral molecule, it always has these tetrahedral carbons, wedges and dotted lines. What if I took those two bonds like C and D here pointing at you, let's say C and D, wedges coming at you, and his point of view was, what if I look and make those C and D pointing at me and then put A and B, top and bottom, in your tetrahedral structure, pointing away from you. So something like this. And therefore, he then saw that if you look far enough away and flatten these out, woo, flatten them all out onto the piece of paper, then you do not need wedges and dotted lines anymore as long as you follow his very specific rules. And that basically is that every Fischer projection has wedges for the horizontal bonds and dotted lines for the vertical. Okay, so this is a way that he could now visualize every single glucose molecule that he ever came up with, or that we can start looking at things like glyceraldehyde and redraw this tetrahedral carbon with the OH and the H pointing out at you. And again, this is the same three-dimensional shape. It's still tetrahedral with two bonds pointing away. If you have any doubt about that, I lost my tetrahedral carbon, here we go, then take a look with your models and do the same thing. Point two bonds at you, the other two pointing away from you, and then squish it flat, and you'll represent any three-dimensional tetrahedral carbon with lines. Okay, so Fischer projections are nice, quick, fast ways to generate three-dimensional representations without drawing wedges and dotted lines. And this made Emil Fischer very happy and allowed him to go out and buy those, maybe those rocking glasses that he's got on. Very chic, very cool, because he could take this messy stereochemical molecule of plus glucose and flatten it now and create the same structure with his Fischer projections, where every horizontal bond is a wedge and every vertical bond is a dotted line, even the ones that are inside the actual backbone. So here are some important notes about how to play with Fischers so that you do not mess up the three-dimensional stereochemistry by redrawing them somehow wrong or wedges, dotted lines in the wrong place. So first things first, structures may not be lifted out of the plane of the paper and rotated just anywhere you want. Like, you just can't take these flat structures and turn them 90 degrees, for example, or it's just, or turn them flat instead of, so we have to be very aware of these things. 180-degree rotation in the plane of the paper, meaning turning this CH3, oh wait, let me show you. Turning this CH3 all the way up and down. That's okay. 180 degrees is okay. And to show you it's okay, let me show you that this molecule is known as S-alanine. Nope, come here. There it is. And therefore, what I can do is to prove to you that I'm not messing around with the stereochemistry, that this really is S-alanine. And I'm going to show you how you can rotate it 180 degrees, and it will still be S-alanine. So it's not turned to R. That's one way you can definitely check if you rotate it, move some molecule in the wrong way, is if it starts out S and you redraw it and it turns into an R configuration, you have messed around in some inappropriate fashion with your Fischer. So this is the first piece of advice I have for you. Always, maybe just blow up the Fischer originally as drawn, giving it wedges and dotted lines. You do not have to create and live in a world of Neil Fischer where you have to look at everything in the plane of the paper. You can make things three-dimensional anytime you want. But to prove it, this is why I can move this molecule 180 degrees in the plane of the paper. Okay? So, whoop, there it goes, 180 degrees around. You don't know how long it took me to do that animation. Oh my God, let's see that again. That was so crazy and so fun. You might have missed it. Now I got the favorite side effect. And notice the H and the NH2 are on different sides of the molecule. So when I flatten it, or wait, just before I flatten it, let me just rewrite it. Pretty looking, I think. There it is. So there it's all pretty. NH2 left, H right. It looks like it's completely different than the molecule on the left. But if I flatten it back out, it still looks completely different. But if you were going to look at the S or R configuration and prioritize this one, is this S? Is this R? This will prove to you that if you did S and R on this, you would come up and find that this final Fischer really is S-alanine. So by rotating any Fischer projection 180 degrees, you will not mess with the stereochemistry. Any other kind of rotations, 90, anything out of the plane of the paper, not good. So just be careful with your Fischers when you're trying to figure them out. And so my best advice is all that S and R. So let's take a little closer look at this. Let's have you practice this a little bit. So here are some Fischers, and what I'd like you to do is initially let's just figure out if these are RRS. Great practice for RNS on Fischer projections. So see if you can blow them out into three-dimensional configurations, and then see if you can take the fourth priority and stick it away from you. Like all RNSs, we like to look at the fourth priority pointing away from us and see if you can figure out if these are RRS. All right, I'll pause the video for you in a second. Stop, figure this out, and then I'll show you the answers. Cool. You ready? This is what I got. So this is not a classroom Jamboard problem. Let's just make sure we're clear about RNSs and then bring this to our Jamboard if you got different things than me. So for the molecule on the left, I got an S. For the molecule on the right, I got an S on the top and an R on the bottom. So this is the RNS configuration. And so what I would like you to do is I'm going to mess around with this one. And what if I put H up here, NH2 here, and then I put COOH. Did anybody recognize that that COOH is really the shortcut for a carboxylic acid? Oh, Orgoland nomenclature, we love it. So I've just drawn this Fischer projection, and I'm wondering, are these two the same? Or are they enantiomers? Because there is one chiral carbon here, and so I'm either changing it to its enantiomer, its mirror image, by changing it from S to R, or I've rotated or moved the pieces, but in such a way that it remains S. So bring this to class. And please post your RRS of this screenshot here and even your three-dimensional wedges and dotted lines so that in your priorities, and so that you can prove to your new study group members whether you think this is RRS and it's the same or enantiomers. Okay? Last but not least, here's another one that's just all yours. Practice, practice, practice. Here we go, launching into more orbital end practice. Tell me if you think A and B are one of these conformations on the right, and which one. And please bring a picture of this actual structure with your final answer labeled A equals what, B equals what, and so on. All right? Okay. This has been our little intro into Fischer projections and the use of RNS to keep our stereochemical world and make sense of it. All right, I'll see you soon. Have a great day. Bye.